Let's look at the application of Le Chatelier's principle to problems where pressure changes occur. So for our problem, we'll use a case study for the decomposition of calcium carbonate into calcium oxide and carbon dioxide. So a common misconception students have about Le Chatelier's principle is they can look at the number of moles of gas on both sides of the reaction and say, all right, if we increase the pressure, the reaction will shift to the side with fewer moles of gas. And that's not entirely correct. Let's look at two different scenarios where there'll be a pressure change. One of them will shift the equilibrium and one won't. The key to really understanding Le Chatelier's principle is to always go to the reaction quotient. So always write out the reaction quotient for any Le Chatelier's principle problem. Okay, so I've written out the reaction quotient for this reaction in terms of partial pressures. So we have the partial pressure of CO2, that's a product, over the standard pressure. And remember that the activities of pure solids and liquids is always 1, so we just plug a 1 into the reaction quotient. So we've got a 1 for the calcium carbonate and a 1 for the calcium oxide. So we've got our one product here, another product here, and we're dividing by the reactant. Okay, now this comes up to be a very simple expression because we only have one thing that has anything other than 1 in the reaction quotient. The standard pressure is 1 atmosphere, so as long as we express the pressure in atmospheres, we can simplify this to just saying Q, the reaction quotient, is equal to the partial pressure of CO2. All right, and that's the key to this entire problem. So let's look at what happens to Q when we perturb the system in two different ways. In our first scenario, let's compress the reaction vessel. So if we compress the reaction vessel, we can see that what's going to happen to the value of Q? Well, the partial pressure of the carbon dioxide is going to increase. Now we should probably be even more specific and say what the change is. Let's do it at constant T. If we don't do it at constant temperature, we know we could change the value of the equilibrium constant, and that would make this, we'd be changing two variables at the same time. So to keep it simple, let's compress the reaction vessel at constant T. So for instance, if we cut the volume of the reaction vessel in half, we know the pressure of carbon dioxide would double, at least initially. So that would double the size of Q. But Q at equilibrium has to be equal to K. So that would make Q too big. Whenever Q is bigger than K, we know that the reaction moves in the backwards direction. So if we compress the reaction vessel, the reaction would have to move towards the left, and we'd be making calcium carbonate, and we'd be reacting these to form it. So the moles of this and the carbon dioxide and the calcium oxide would go down, but the moles of calcium carbonate would go up as we respond to a compression. So that's the first scenario. Now we could increase the pressure in our reaction vessel a completely different way. We could keep the volume constant and just add some other gas that doesn't react, something like helium or argon or something like that. You'll notice this doesn't change the volume of the reaction vessel, and so it doesn't change the partial pressure of CO2. And the partial pressure of CO2 is the only thing that affects the value of Q. So even if we triple or quadruple the total pressure, we don't care because it doesn't affect the partial pressure of CO2, and so it doesn't affect the volume of Q. So this would actually have no change on this equilibrium. So the number of moles of calcium carbonate and of calcium oxide and of carbon dioxide would remain constant regardless of how high we made the pressure inside the vessel, because it's the partial pressures that matter, not the total pressure. So be careful when applying pressure changes to Le Chatelier's principal problems.